actually replace this particular concave function with a upper bound which is linear. Then with these two steps, now you have this form in which you have a sum over each exponential, and in each exponential you have only one argument, one theta. Okay, and that's the trick. And then when you take a derivative over the theta I, you get only one term out of it. Okay. And then we have all these rearrangements. I hope you get clear. Maybe what's coming from here and here seems to be unnecessary, but that's the convention in the book. So here you have on the top a empirical expectation of one feature, and here you have the true expectation of that feature, and that's where we say inference learning is also hard. It's as hard or harder than inference, because to compute this expectation, you need to do what? You need to do the expectation over only the clicks captured in this feature, right? Which is a inference step. You need to compute the marginal of a subset of random variables, right? Let me just make it more clear. This one, generically, it corresponds to really x fi over x of c, which c is a subset of features, variables that you want to define a potential function on. Okay, and computing an expectation over that means that you need to sum over many other configurations, which is difficult. That's why we need to do inference. From here to here, it is not necessary. I copy it down just for the sake of respecting convention, because here this p sub t is sometimes known as the unnormalized version of the p. Sometimes you don't want to. People actually prefer to treat this differently if this one also gets an unnormalized version. But we don't want to discuss too much about that. It's just a computational convention. And then with all that, you can see a update rule, which I put it in here, which is very similar to IPF. In here, you are rescaling the potential functions represented in a tabular form. In here, you are representing the true distribution, and here, you are rescaling that with again a ratio between the empirical expectation over feature versus the true expectation over features. Okay, so this one is the expectation of marginal, the empirical marginal. This is the true marginal. So these two are kind of correspondent, right? And the update rule here is very kind of straightforward. You have the theta updated by a log of the ratio between the expected feature and the empirical expectation of feature and the true expectation of features. Okay, so hopefully that gets you straight, clear. Then this IPF and the GIS are essentially the same thing, although they were used to update potential functions defined in different ways. Okay, yeah.
So you need to remarginalize every so often to take the new.
That's exactly the situation.
How often do you do that?
In each iteration. That's why learning is very complicated. In each iteration, you need to redo the inference. Okay, you redo inference to do expectation or margin or whatever, and that's of course very complicated. It could be complicated if you had a very large graph. All right, so now let's move on to actually study this, embedded inference problem at a greater extent. Okay, so from the previous example, you already see that inference is actually embedded already in learning, even in fully observed graphic model. And now we're going to see some other graphic model where you really need to do inference no matter what. Okay, and that's basically happens to what we call the partially observed graphic models, right? And I think we have studied the examples quite a number of times already, right? This is a hidden Markov model which we use to, estimate, phonemes or other latent tags or labels of sequential data. And surely we understand that, this model is only partially observed. We only saw the signal, the measurements. We don't actually see the partial state, the latent states, right? Sometimes you're lucky if they give you the entire thing, then you can do a supervised learning, which we actually talked about last time. Supervised HMM sometimes could be done if you have a good training example. But in reality, you only probably have this sequence X. Then you have to have another algorithm. And I just throw at you some other examples. This, in biology, people, always worry about inferring our ancestors. or telling stories like 7 people coming out of Africa and stuff like that. So all these stories are inferred actually by a latent graphical model where the ancestors are treated as hidden variables. So now let's use this simplest case to start, unfolding the mathematical formalism of this inference problem. And the model is well known as a mixture model, and you will see why it's called mixture model in a second. The question, the empirical problem it tries to solve is this very well-known problem called clustering, right? So I have this cluster here, and again, let's agree on one thing. Let's forbid us from asking how many clusters. Okay, I know this is a very important question people always want to ask. Let's save that for later. Suppose let's know we want to say 3 clusters or 2 clusters. What should we? How can we do that? Right. So, okay, suppose that it is a 2-cluster problem, and if you see the data, it is pretty obvious. You have a cluster on this, you have a cluster on this, and then you may be able to write down, a assumption where this one may follow some kind of a Gaussian with 1 mu and 1 sigma, and this one follows another Gaussian with another sigma, another mu, and so on, right? But how can we estimate that? Well, if you see the problem, estimation becomes a supervised problem because you can pretty much group the points in here, you already finished the label. The real challenge comes from, say, you are giving just a data set where you don't actually visualize it, okay? And then you have to be able to take on every data point. This data point is not known in terms of which cluster they belong to. You have to do some guesswork. Okay, so that's the setup. And so this kind of model is interesting because they deal with this so-called multi-model estimation or modeling, where you have multiple modalities in data, which is pretty common in real data world. So the kind of beginning point is to start introducing some auxiliary random variables. And here, for example, we call our observed value, which is the coordinate of every data point. Say this is a x1 equal to 2 kind of coordinate. We call them a observation variable. And then on top of that, we associate with each of them a label called z. Okay, it's a discrete label. It can be anywhere from 1 to k. Suppose we know the number of k's. And then giving you any data point, you can probably imagine they can belong to different type of modality or different, we call them mixture components in a mixture model, which is indicated in all these little Bell functions. Okay, so how can we write that down? Well, I'm going to show you very later that each of them xi. If you already know the zi, then obviously it is belonging to a Gaussian distribution indicated by the z, because the z is the indicator of the index, and then you can select among all of them just by multiplying together, right? But if you don't actually know the z, you don't actually know, you only have the x, and that actually makes the whole thing tricky, right? I can just flash at you the outcome, and then we can derive it. As you can guess, this likelihood of a single point without knowing its belonging of the cluster membership equals to now a summation over a weighted sum of little Gaussians. Okay, and this pi is basically the probability of each Gaussian being plausible. Okay, and here are some kind of little high-level motivational slides on why this kind of problem become necessary and important, right? So in fact, you run into latent variable problems in many, many different contexts, and here I give you just a few examples. Sometimes you truly cannot observe something. You cannot fly to the sun and measure temperature there, right? It's too hot. And sometimes this latent variable thing is not a real thing. It is just a vehicle for you to make sense of data, such as a cluster label. It is, not really a physical entity. You can label it 1, 2, 3. You can call them A, B, C, or you can make 2 and 1 to be the same label. It's really arbitrary. But these latent labels give you some easy way of interpreting real data. And in particular, in our modeling framework, we categorize the latent variables into 2 big families. One is the discrete latent variable, which are typically cluster labels, some topic indices and stuff like that, right? And then there is this class of a continuous latent variable we are going to study later on. It's a little bit more fancy, more complicated, which actually corresponds to something nowadays very popular. You may heard, Google were, building a project where they want to do the so-called word embedding. They want to turn a word into a vector of something, and then you can measure distances between words or do other things. That latent vector is one of these continuous latent variable. Okay, it's an embedding in the latent space, which may carry, semantic meaning. Sometimes they don't have any meaning; it's a geometric embedding. But anyway, this is a typical latent variable, a continuous latent variable inference problem. So now let's look at a Gaussian mixture model in our simplest case. This is a Gaussian mixture model. In the discrete, in the 2-dimensional case, in the 1-dimensional case, you just draw a density over, either a group of points or a single point. Then, if you just, look at the cumulative kind of a probabilistic mass, then you probably can see a curve like this. The nice part of that is that this density function is now, sometimes we call them semi-parametric. Okay, if you define the Gaussian bump on each data point, then you can model density function of arbitrary shape, right? Assuming a Gaussian distribution is very often inflexible because they just have one bell shape, and many data do not distribute like that, right? But in here, you can show to yourself that it can capture any shape of density function, and this is the equivalent in a 2-dimensional space. And in the graphical model sense, we use this graph to represent, both a generative process and also the dependencies between random variables. And very often we put a plate on top of it to indicate the fact that you have n copies of such data. And as I said, the density function, okay, of this kind of distribution is now written as a weighted sum of specific densities under a single Gaussian function of that data point. So some terminology, this is called mixture proportion, mixture weights, or something like that. And this is called a mixture components. Okay? And again, this is called, it's used for unsupervised clustering. I use this very cumbersome word in order to respect the literature and convention. It's kind of redundant. Clustering is by definition unsupervised. You don't have supervised clustering, and you don't have unsupervised supervised. Supervised classification is also weird because classification is by definition supervised. But again, if you look at especially papers in KDD or in the data mining community, this kind of redundancy or even confusing definition can be found anywhere. It's kind of annoying. But anyway, just make sure you understand what they meant. All right. So now let's say formally, where does this density come from? Okay, is that just by a pure kind of intuitive guess, or you actually have a clean, principled way of deriving this? For example, what if I don't want to assume a Gaussian? I want to assume each component to be some other thing, a t distribution, or in discrete case, a multinomial or stuff like that. How should we do that? Right. So here's the idea. Very, very straightforward, but I want to just show you. We have this 2-node graphic model now. And again, using our Bayesian network, building blocks, we have a marginal over the parental node, which we call them a multinomial because it is an indicator function of, class membership belonging, right? They must be a multinomial distribution. And that's the way I parameterize it. Each pi I is the prior probability of that label being in one cluster. And then by definition, in graphical model, for the next one component, we need to have a conditional distribution of the child given the parent, and therefore this is that conditional distribution, which is now called a conditional Gaussian. Okay, and you have all this proper parameterization. And then once you have that, the first thing we need to do is to write down the joint of the graphical model, right, which equals to P of z given times P of x given z. Therefore, you put this and that together. Okay, just a straightforward kind of application of that factorization law. And then given that, you are going to now realize that z is not observed. Therefore, it is illegal to write this as a objective, because a objective has to be something that is only dependent on data and nothing else. It should be no longer a variable itself. The object shouldn't change, basically, right? So we need to get rid of the randomness in here, that the z should be marginalized. So we get now a marginal likelihood where we sum over all possible values of z, in which I use a slightly cumbersome but more explicit reparameterization. I basically use the z as this indicator vector. Okay, and once you do the summation over all k, you actually will get down to this form, where this one is the probability of z equal to every label, and that one is the resultant mixture component selected. Okay, clear about that? Okay, now let's see what do we gain, what do we lose. Okay, so what do we gain is that this density function is rather rich. As I said, it has multiple kind of modality. It gives you the power of modeling data. What we lose is that this loss function is no longer a nice behaving factorizable thing, right? Remember, one key kind of advantage we want to leverage from a graphical model is this property, where once you write down the joint, you can always decompose them and do local estimation of the variable states. But in this case, you have the likelihood like this, and you can try taking the derivative, or do other things. You will find it's not so easy to deal with. Okay, you have the logarithm and the sum within the logarithm, so that they are not decomposable. Okay, so that's the first message. So what should we do? So here, let me just give you a wild guess without any theory, and to lay out a algorithmic idea. Okay, sometimes people call EM algorithm a heuristic, because depending on the way you present it, depending on the way you make use of it, you don't need to understand any statistics, basically. Or you may even be able to tell a wrong statistical story if you use it uncarefully. But nevertheless, you can still use it. And here's the idea. So I'm going to now put down this notion of, again, pretend that we have the full data. Okay, we don't have z, right? But pretend that we have it. We just shade the z. And then we can write this so-called data complete log likelihood, which have this very nice factorization form. And you have MLE, over this, and give you very intuitive guess of an estimator of the mu, the sigma, and the pi, which are basically sample average, sample mean, stuff like that, right? Okay, so now we ask, what if we don't see the z? What should we do? Okay, so people could imagine that if we actually know the whole model already, we already know the model. Forget about our goal being learning. We learned already with all this. Then the task of figuring out the z, if we don't know z, we can actually figure out what z is by just writing down the posterior of z given x based on our current estimation of the model, right? And then once you have that thing estimated, you can basically replace the z with a surrogate of the z. It could be the mean of z or something, or the map of whatever, right? And then you just, how about plug in this into here so that you still turn this whole thing into a kind of a, very concrete objective. And then you start to change your kind of context. You say, okay, now I actually know all the data, but I don't know the parameter. I'm going to ignore my previous version of parameter, and then let me repeat. Okay, so this is basically the basic idea behind this EM heuristic. So how to upgrade it into a theory from a heuristic? right? And machine learning people sometimes feel embarrassed being called using heuristic or something like that. So, okay, so here are some proper questions to ask before you can actually upgrade it. First, in the E step, we want to ask, E actually translates to expectation. So there are naturally at least two questions to be asked about expectation. Right? One is about, what do we take expectation weights? Expectation assumes a distribution. So what distribution we want to use? Okay, and the expectation is taken over what? What kind of a quantity we want to take an expectation on, right? So these are the two things. And then the the M step, we also need to understand now maximization of what? Are we still maximizing the likelihood or something else, right? And maximize with respect to what? There are many, many arguments in this whole thing, and what thing are we changing to maximize? Right? So the rest of this lecture is to get you straight on these few questions so that now you can tell people a theory about EM, and in fact you can go beyond the mixture model. Okay? And especially this question about interpretation can be very, very subtle. You will realize that many of the kind of the trivial way of telling EM can be wrong. For example, you may have heard stories like, especially from practitioners, they say, EM, well, I know how to do EM. EM is about replacing whatever you don't know with expectation. Right? Very almost right. But the truth is that, do you want to, for example, do a expectation over that thing you don't know, and then, then make a function out of it? Or you actually want to do this and the expectation over the function? This kind of thing can make a difference. Okay. Usually the naive thing people do is to always turn x into E of x, which actually will get you a wrong place if you are not careful about certain models. Okay. And we'll see examples from there. All right. So algorithmically, we actually saw something very similar to EM before. And here is an example so that you can kind of make a connection on the algorithmic design of EM. So remember the K-means algorithm, we kind of all know that. It's also designed for doing clustering, unsupervised clustering. And that's basically the context. And I argue that in the K-means algorithm, you are doing almost a EM type of thing. Okay, especially except that the E step is a little bit peculiar. It's not really doing a typical E that way you really call excitation. So that's what we do. You want to first assign, you want to have a random guess of the centroids in a cluster, right? So you begin by some kind of weird version of, this, and I put 0 here to indicate the initial guess, right? And then once you have that, say we place it here and here, you can now start assigning labels to every point, right? And the mathematical, what do we mean by assigning labels? I argue that assigning label is about solving this optimization problem, this maximization problem. You are computing the index, the assignment of X label, so that, or maybe you are optimizing over all possible choices of the mu so that this function is minimized, right? You basically assign the point to the closest center. Right? Mathematically, it's written like this. And then you are going to have the z estimated, okay? And then what you do is to recompute the centroids. Let's forget about the variance. Suppose it is just, we only care about the center, for example. You could care about variance as well, but we don't do that here. And then you are going to recompute. Recompute is actually done by this step. You are going to now, basically compute a sample average of the points belonging to that particular cluster. And mathematically, it is really about running through an index function where you select points based on whether the label agrees with the points of the cluster being selected, right? And here is the total number of counts in that cluster. Okay? So, all these equations looks rather cumbersome. This is probably not what you do in your MATLAB code, but they expose actually the commonality of this operation to other operations we're going to do later on very nicely. Right? And so at the end of the day, you are going to do this iteratively. Right? After you do this, you're going to reassign that, and then you redo this, and on until you reach convergence. That's basic k-means. And the EM algorithm is very, very similar to that. Right? The starting point is the same. You're going to start from unlabeled data, and you now also start by picking the mu and the sigma for given number of clusters. And but what you do, in terms of assignment is a little bit different. If you remember, at least what I told in the 701, or maybe I think somebody else are telling a similar story, is that instead of giving a discrete assignment of every point in this problem, you're going to give them fractional assignment. Right? So basically, for every point, you're going to compute the probability or the fraction of likelihood of this point being in one of the possible clusters. So each z, suppose I still call the assignment z, is now getting a vector of assignments. The vector components sum to 1. They are all fractional numbers. Okay. And again, based on the fractional numbers, you are going to now recompute the centroids. And in this case, the centroids are computed by counting every points, because every point have some non-zero fractional assignment, right? And do I have an equation of the algorithm? I think I have, right? So, oh, I don't. Okay. So I'm going to write it here. So what you have is that this new mu of of iteration 1 is going to be now x, okay, weighted by that fraction z. Let's call them z hat, okay, I, and sum over I. Yeah. So this z is basically a that fraction. And what that fraction corresponds to, if you want to turn it formal? How can we compute this z in the EM algorithm? Well, expectation, right? That's how it's called. It should be the expectation of the label. And what is the expectation of a label? It is the posterior probability of z given x, right? All right. So we're going to, of course, to compute the posterior probability of x, you need to supply the current version of the model, which is the mu and the sigma of the current estimation. And then you compute the posterior, and then you're going to jump into here and recompute the next version of the parameters and so on. Right. All right, so these are just a very, very high-level heuristic story. We'll see actually more beautiful equations later. But now let's see what actually happened. Okay, I think this slide is, it's basically giving you some mathematical pictures without giving you why it is right. So we have this, model, and we actually have this likelihood, which we said it is not, easy to differentiate. And so we are going to introduce some quantity called the so-called expected complete log likelihood. We said that originally we don't like this term inside the bracket because it is not a fixed constant, right? And the problem is z. Well, the easiest way is to get rid of z by taking the expectation over that, okay? And with that, you actually now see the whole thing boils down to a factorizable thing, okay? And where each unobserved random variable is now replaced by their expectation, okay? So that's basically what motivates the EM algorithm for mixture of Gaussian I said earlier, okay? You actually are choosing a slightly different likelihood function or objective to optimize. So until now, I don't know whether you get more clear or more confused. Basically, we have an algorithm. We also have a story telling you what the algorithm is doing. It's actually doing this, optimizing the expected complete likelihood and so on. Do we now have a general law or some kind of justifiable theory behind all this practice? For example, why do we think doing this is correct? Right? Why not choose something else? Right? So you may have this kind of question. All right, so now let's actually maybe wind down a few more steps before I actually tell you the general insight behind what we did. Yeah, so here is the equation for computing that soft assignment of z, which is indeed using the posterior probability of the label given the data. And you can easily do that by applying the previous version of the parameters and the data. And in the M step, now you can pretend that your data is totally observed. Then you just replace the original law of pi estimation, mu estimation, sigma estimation, with their z replaced by the expectation of z. Okay. All right. So I think so much for the whole story. And here, before I move on, I want you to remember this side-by-side contrast between the k-means and the EM. They are the same thing, okay, except now that my definition of the z assignment here is, you can call it a map assignment, okay, and here it is a expectation assignment. Okay, that's the only difference. Otherwise, they are the same. So by nature, they are both iterative algorithms. Why, in many cases, EM algorithm is more popular, or at least more popular among the theoreticians? Well, that's because there is a very nice story behind that. So how does the story go? So this is our loss function, and it is not easy to deal with. And we want to actually figure out why it is, how to make it more easy to deal with. Okay, right. So here is a kind of leap of faith, and also a very, very kind of dramatic kind of jump of our insight. So this whole thing is a very nasty function, which is, first of all, it is multimodal. You will probably notice that this is, a log of a function that is like that, right? It is a mixture model. It is multimodal. Then it is also wrapped outside with a log. It is an extremely nasty function to optimize, right? So we need to do some surgical kind of operation on this, hopefully to make them more easy to deal with, like what we did in the GIS algorithm. So here is a trick. Let's first introducing some general notion about the expected complete log likelihood. Okay. After all, we actually like the complete log likelihood over the true likelihood, because the complete likelihood is a factored kind of a multiplication of many components. Okay, and if I don't sum over the latent variable, I'm actually in good shape. I will actually have a factored objective. So now let's take this as a candidate objective, but I want to remove its randomness introduced by the latent variable z by taking the expectation over z using arbitrary distribution over z, because I don't actually know z. Z is something that I don't observe. Right? So to begin with, I'm going to introduce this q, okay, which gave me this term. All right. So q is a distribution over z. And suppose, for simplicity, let's assume z is a discrete vector, right? Then, we have some nice properties of z, right? Of qz. Qz basically, you can imagine qz basically is almost like a vector of, pi 1 to pi k, in which each pi I greater than 0 and the sum over pi I equal to 1, something like that. This is definition of probability, discrete probability. So that actually allows us to apply an important law called the Jensen's called again. Right? So we're going to now define, in this case, a lower bound of this not a concave anymore, a convex function, okay, by actually introducing some approximations. So here is our original complete likelihood, okay, and we're going to now introduce two auxiliary terms, upstairs and downstairs. Basically, change nothing, but this one is basically an arbitrary distribution of the z. Okay, I'm not saying it is the true process. It's an arbitrary z. And then I can take this entire thing as one term in the argument. Okay, and then what you can see now is that inside the log, there is a convex combination of the second term. Okay, and this is basically the shape of that log function. And any point in here is what? It's basically a convex combination of of some function. Right? So this is basically inside the log. And the Jensen's inequality said that that function is upper bounding a term where you take out the z and put the log of f inside. Okay? So that basically corresponds to this point. Okay. So this point corresponds to what? It corresponds to basically these two things, which are the original, f okay, and this is basically, the convex, the one in the middle is it is on the line, therefore it is a linear convex combination of these two things, and the weight are defined by this qz. Okay, it can be arbitrary qz, because with your change of different qz, you're only going to change the position of this point from here to here to here to here. It will be never outside of this line, right? Remember, qz is between 0 and 1. Therefore, this point will never be outside of this segment. And therefore, must be upper bounded by the original function. Okay, so that's the insight about Jensen's inequality. So this will be a lower bound of that. So what's the big deal of that? Well, the big deal of that is now inside the log, you have not the likelihood of data. Instead, you have the symbolic, at least, complete likelihood of data inside the log. That's actually a very, very important move, because if you have the sum inside that, you lost the factorizability. All right, so we're going to now call the first term, okay, the complete log likelihood, the expected complete log likelihood, which basically is this part. Okay, and of course, the second one is the entropy of the z function, which is resultant from this one going with this one. Okay, and remember, entropy function is always what? It's always positive, right? Therefore, you can remove that and define a strict lower bound, of the original likelihood. Okay, so after all this derivation, we at least established a fact that the complete log likelihood is upper bounding this f function, which is the sum of a expected complete log likelihood plus a entropy of the hidden variable. Okay. All right. Then, without the proof, I first claim a good news. It turns out that the EM algorithm is actually estimating, optimizing this one, this f function. Okay, and using almost like a coordinate descent style algorithm, in which in the E step, what's happening is that this f function is actually optimized, okay, with respect to the Q, the choice of the latent variable distribution. Okay, and then in the M step, you are going to keep the Q fixed, and your other argument of free parameter is the theta, and you're going to optimize with respect to that. Okay, and that gives you a picture about this. Okay, all right. So that's the first news. EM is actually now optimizing a lower bound of the likelihood function. Isn't that great? No, we are originally trying to optimize this guy, or maybe a funny shaped one, and we couldn't do that. Now we find a lower bound of that. We are hoping that pushing up the lower bound is like pushing up this function originally, because both of them at least is a argument, is a function over the. Actually, let me say it again. This one, the original function, this function we want to optimize is a function of the theta, right? And this auxiliary one f is a function of both the theta and the q. right? So we introduced something auxiliary, and then we were able to push up the lower bound, the lower bound of the original objective. The second one is actually even more interesting. It turns out that what you are actually do in the EM algorithm is not only about optimizing a lower bound of the data likelihood. You are actually optimizing the data likelihood itself. Why? Well, it's because when you actually are doing the E step, you are, estimating among all possible distributions of Z, which distribution is maximizing the F function. Okay? So by inspection, if you have the freedom to choose this Q in arbitrary way, what actually is a choice that maximize this term? Yes. Okay. So if you actually fix that Q to be the posterior of Z given X, you actually will realize that this F function is now equal to the likelihood of the data. Therefore, the gap is closed. Okay. So go back to the picture here. What you really do is that by introducing some auxiliary term, you invented a lower bound of the original objective. But by choosing the Q in a smarter way, you first close the objective to here. And then you push up, again, this function with respect to theta even upper. Therefore, you are actually optimizing the theta with respect to the, to push up the likelihood of the data. Okay. So that's a subtlety behind EM. Many people probably didn't get to that far, but I want you to realize that. And the proof is extremely simple in here. It's just by inspection. And then, in the E step, okay, now just by inspection, we know that the maximizer, okay, of the F function with respect to all possible distribution over the hidden variable is the posterior likelihood of the hidden variable given the data. And then you are going to bring that back to our objective. So this is our original objective, okay? And you bring back this Q to be that P of Z given X. Then what you get is actually this. Okay, we can make some assumption. For example, the joint likelihood is a exponential function, and the conditional of the observation given the label, the latent variable may be a Gaussian function. In any case, you will have in the loss some linear combination of sufficient statistics from the data and sufficient statistics from the hidden variables. Okay, that's basically the high-level message. You can review how these are put together by going back to the lectures we went before. So at the end of the day, you are going to apply, plus it is a Gaussian function or an exponential family function, which is giving you a kind of an extra benefit because you are talking about the log likelihood of that. Therefore, taking the log over a Gaussian or over a generalized exponential family function, you get a kind of a linear combination of things, of sufficient statistics. You don't have any other nonlinear terms. Then taking the expectation over that is really about taking the expectation over this one. This one is the sufficient statistics of the Z. Okay, not really the Z itself. Again, that's another insight. In the E step, by introducing the optimum posterior into the loss function, which is the expected complete likelihood, what you actually get is the expectation of the sufficient statistics of the hidden variable, okay, using the posterior, not the hidden variable itself. Sometimes, in certain design, the posterior, the sufficient statistics is the variable itself. Right? We see that example before, but in many cases they are not. Okay, and that makes a difference. If you just insist on making the expectation over the variable itself, you actually will lose the guarantee on this lower bound of likelihood. They may be actually fluctuating around the bound. All right, so where are we? So we have the M step now. So now this one is taken care of, and the only remaining argument is basically the theta, and everything go as usual. You actually know how to do the M with a fully observed model, and here everything become observed already. So that's the usual kind of EM algorithm. Clear about that? Any questions? Yeah.
Can you explain a bit why the Q(t+1) is the optimal posterior Q of Z?
The optimum Q of Z. It's because, okay, let me see. It's in here. All right. We said that F is a lower bound of the likelihood. We already know that. And just by plugging in this, we found that this one equals to its upper bound. Then you cannot go better because this one is, smaller or equal to this. Now I made them equal, and that means this choice is the best you can do. So that's why I say it's proved by inspection. There is no derivation here. You kind of guess the result, and you show it, and there is no counterexample, basically. Other questions? Yeah.
Can you go back 2 slides?
Yeah.
There you define the expected complete likelihood as being the sum of Q of Z given X and theta.
Yeah. That's an arbitrary posterior, not the true posterior.
Oh, that's there.
Yeah. In fact, I shouldn't even write this way. I should have written just Q of Z, arbitrary Z.
Oh,
Okay. Yeah. I kind of use P of Z given X as the true posterior, and Q could be something else. All right. Any other questions? This is the only challenging little bit in the EM algorithm. If you are okay with that, comfortable with that, you are fine now. So there is nothing special, mysterious about EM anymore. So maybe we should go over a few examples just to enhance your familiarity with that. So let's look at the EM for HMM, for example. Okay, and HMM is actually one of the most successful non-trivial application of the EM, even for that application, it's already not called the EM algorithm. It has a new name called the Baum-Welch algorithm, right? Right, so this algorithm, you probably heard about that. It is completely exactly a EM, although I think the Baum and Welch did not, actually, I think they probably invented this algorithm earlier than the EM paper, just because they are very clever and treat it as a heuristic way. But I'm still puzzled to why they actually come up with this. So what's happening is here. You have the data likelihood, complete likelihood, which is obtainable by multiplying all the little terms as we did before. And then realizing, X, Y being unobserved, suggests that you want to now use a complete likelihood. Okay, so expected complete likelihood. Therefore, you introduce expectation. Basically, you introduce a posterior on anything you don't observe. Okay, so that's basically what you have in here, and that makes the whole thing decomposable into, again, local terms.
Is there an error with the last term in the upper equation, the first equation?
Is there an error? Where?
The last term of the first equation.
This one?
It should be P
of X, yeah, sure. Let's see. P of X given Y, sorry. Thanks. All right. Yeah, so at least you know this and that, right? That step. So now the whole point is to compute, you have this singleton, hidden state. You have this pairwise hidden state. You have this, again, singleton hidden states. And these are typical, quantities resultant from this term, that term. Now the challenge is at how to compute their expectation. So for that, it's clear that we need to compute the P of Y given X 1 to T, the entire thing, over X1, right? And do we know how to do that? We learned that from our inference class, right? It is the inference. It can be done using forward-backward algorithm. Okay. And we also actually know how to compute Y of I, basically any hidden state given the entire sequence, right? But what you have in here is a pair of hidden states. What should you do? Well, some people suggest that since we know this, we can basically compute a Y of T and Y of T plus 1, and I'm going to multiply them together. Okay, that's a suggestion one would easily adopt. So unfortunately, this is wrong. Okay, it's wrong because this does not equal to this. That's it. Okay. So what you really need to do is to compute a p of yt and yt plus 1 given the entire sequence. Have we learned that? I don't remember I taught that. But on the other hand, we should know how to do that, right? Because now we are, instead of asking for a marginal potential over a particular node, we are really looking for a potential function over a pair of nodes. Meaning that in your message passing or in your junction tree or in your whatever belief propagation algorithm, you just define a bigger message. The bigger message now contains a pair of random variables. Okay? And then you should be able to derive that law almost identically as what we derived before. I meant to give that as a homework question. You want to do that. But I guess the homework is already given, so maybe as an extra credit sometime, okay? So basically, that can be done in a polynomial time. So at the end of the day, you're going to compute the expectation of the pair and also of the singleton. And then you plug in to the table that we used before to compute supervised version of HMM. Okay, and then you get estimate. Okay, so that's basically EM algorithm for a hidden Markov model. You have the E step, you have the M step. And by the way, this is not the end of the story. Okay, once you have that, what should you do? You should go back and recompute this, right? Because that one is based on the current version, and you have a newer version. So iterate until converge. Okay, just for your information, I think down to the later part of this lecture, we're going to tell you even a newer version of inference in HMM. This one remains some people still call it a heuristic, because even though it has a theory, it does not have the theory of convergence to a global optimum. Okay, and why? Because the loss function, this guy, is a non-convex loss. Okay, and for non-convex loss, you have this coordinate descent algorithm. You are only guaranteed to convert to a local optimum. Therefore, in practice, when you do a Baum-Welch, when you do an EM, like in k-means or in clustering case, what you really should do is to randomize the operation by reinitializing the whole thing multiple times. Remember that? Every time you reguess a new thing and run the whole iteration, converge, you remember the results. And in particular, not only you need to remember the results, you need to compute this term, which actually gives the value of that objective. Okay? And then you reinitialize with some other random number, and then you converge, and then you also compute that number, and then you compare a bunch of such convergent point, and you pick the best one. Okay. Usually I do 30 or 100. And when many of my collaborators come to me say, hey, I use k-means, I run some cluster, but how come each time I have different results? Then I told him, well, you're supposed to see different results. You're supposed to run multiple times every time. And then when every time you still run multiple times, you are likely to pick the same result. Right? So that's kind of the way you debug a EM algorithm. All right, so we have that. And we can certainly turn this idea into a very generic one for general Bayesian network. Right? So here I have a kind of a pseudocode for that. Basically, you're going to run through all the nodes in the Bayesian network. And for whatever nodes that is partially not observed, you run the inference procedure to compute a posterior of that using hopefully either a exact or a approximate inference algorithm we're going to talk about later to impute that. And then you have this, and then you run the M step with a fully observed graphical models. Okay. So for partially observed and direct graphical models, it's a little bit tricky. I invite you to think about how should we deal with that. Because we said last time, when you observe everything, you still need to do the inference to compute local marginals. Now you don't observe some of them, what do you do? Okay. So there is a double kind of loop, where in the outer loop you need to infer, in the inner loop you still need to infer. And that's something you want to figure out. All right, so this is a summary of the EM. And I think the main message is that you have a justifiable loss function. You have this iterative step, which is a coordinate descent over the distribution space and over the parameter space. Okay, and that's it. Okay, so any question? I have some additional, actually, some additional material, some traits I want to give you in terms of model design. But before I go that, I want to make sure you understand the whole material so far. Any questions? Okay, let's have some desserts then. So let's now, with this tool, I want to introduce you a few fancy latent variable models, which can be very simple, but they still, can be very, very useful. And along that, I'm going to give you the EM derivation of how they can be learned. So we often are interested in something called expert models. I don't know why it's called expert models, but basically it is a latent space model like this, almost like a mixture model. You have x to y, and y comes out of some function of f. Okay, and that function could be a linear transformation. Imagine you have a loading matrix, then this is an embedding, and you load the embedding to a real data. Okay, so that's the typical kind of baseline mixture model. But sometimes I want to make it richer. I basically say, what if I'm in this scenario, in different regimes of x, I'm going to use a different loading function or a different transformation. And I don't even know where my x is yet. And that's basically a picture depicted in here. Right? If you have a density like this, how are you going to fit it? Okay. So here, the art of design of graphic models really kicks in, and I want you to actually be fluent with this art down the road. Okay. In terms of how to introduce random variables in a sensible way. So here, I think it's illustrated in Michael's book already. You introduce this z, which is an auxiliary latent indicator. It is dependent on x, meaning what? Meaning that you are going to look at the value of x, in here and here. Depending on that value, that sign of the z or the label of the z may flip. Okay, maybe in this region the z takes a value 1. In that region, z takes a value of k of 2. You don't actually know. Okay, and then this x and the z will jointly decide on the y, meaning that depending on my choice of the z of the f by z, I'm going to use a different function to fit the function from x to y. Okay, so that's it. This is just totally by design. You can argue it's right or wrong, but if you like this design, then there is a way for you to write down a joint graphical model. Okay, for example, here you can have this z indicator function using something called a softmax function, which is a multi-way sigmoid function. Remember what is a sigmoid function? It's a logistic function we used for predicting binary probability. And the sigmoid is a multi-way probability prediction based on the same kind of 1 over epsilon exponential of something. Right? And then conditioning on that, you have now x and z. Z is only an indicator helping you to select one of the possible Gaussians, conditional Gaussians. Okay? The Gaussian mean is defined by the latent x times a loading matrix, a loading something, and then you have different choices of that loading function. And you can write down, of course, the posterior of the latent variable very easily by just working on all these derivations. And that gives you something called a mixture of expert. And that model is solved by EM algorithm. Okay, know that algorithm now? And okay, so I can even suggest you some fancier versions of that. You probably will be amazed how I can play with the graphic model in that way. So I have this. How about I also have that? I can run an HMM on that. Sequentially, my emission model now becomes a mixture of expert. And that's actually another fancy combination. I used to do this as a homework in Max class to derive the equation for that. It's not really difficult, right? It's just some additional little trick on top of the on top of the Baum-Welch algorithm. Right? And you can actually replace them with even something called a common filter, a mixture of, you can be infinitely complex just by playing all these tricks. All right, that's one line of idea. The other thing is called what is known as the conditional mixture model. I don't know why it's called conditional. It's probably conditional regression model or something. Anyway, in this case, the x become observed, and but your little choice of what function to build a regression on is still unobserved. And same thing, you can introduce this latent function here to select different regression function, and this softmax is the selector, and you can run EM algorithm again to do that. Okay, so mixture is a very important trick in case you want to build a condition-dependent way of modeling data or introducing functions. And here, the EM algorithm is an indispensable tool for dealing with these type of indicators. Okay. The story can go on. I think many years ago, Jeff Hinton visited Berkeley and showed us this graph. We were all completely confused at that point. It's called a mixture of experts. And then again, all these names is very, very fancy. But you can already see the shape of roughly a deep network type of architect, right? So same thing, here, that's the kind of generative story. You have the feature. This is actually directly coming from here. Instead of having one label, he now has actually not even two labels, but a sequence of labels in the form of a tree. In a sense, I'm no longer in this linear regime that here I have one regime, here I have one regime. I'm in the high-dimensional space where different little area is carved into a particular space or subspace where a specific regression function should be used. And to organize that, basically people say, let's do a hierarchical division. Let's cut in here first to divide the whole space into half, then cut here and cut there to divide further, and so on. So this is a tree cutting procedure, right? And then these are the labels. This is the root label, the sub-leaf, the leaf label, and the sub-leaf label, and so on and so forth. And you can basically introduce this sequence of latent variables. By itself, they actually can observe a latent tree distribution. Okay, so that's what's depicted in here. And now we know that already. We know how to do exact inference on tree, right, which is using the message parsing. Therefore, hidden variable isn't really a big deal, at least for the EM kind of heuristic to deal with. And yet another example, which is called the mixture of overlapping expert. Now, this is kind of interesting. So now we don't have this interesting kind of space-dependent requirement of a different regression function. For example, in X, whether it is in here and here, we don't really choose one of the possible options to do the regression or to do the emission, for example. Instead, we are going to assume that no matter where my X is, remember, X doesn't have to be on a line. It could be a high-dimensional space. No matter in which area my X is, I want the mixture, the regression model to have a multimodal behavior. Okay, and if that's the case, then you have this. You have still an indicator, but your X is no longer controlling the Z. All right, and that's it. Very, very simple. You remove an edge, you suddenly create a model like this. Okay, depending on where your X is, you may be using this line or that line, but marginally you are using two lines or two functions to fit the output. Okay, yeah.
In that model, is X not observed?
The X can be either observed or non-observed. In this case, it is not observed, but this is just a design choice. Yeah, if you, for example, you plug this into a HMM setting, that X is not observed, but you can still use this kind of trick. Your emission model becomes like that. In regression, you have everything observed, right? So by that, I really meant to encourage you to be very flexible. You can color the nodes, or you can shade the nodes in whatever way you want. You can remove very surgically an edge here and there, or add one here and there, just to create totally, differentially behaving models. Like look at the density in here and the density in here. They are totally different, right? But the building blocks are very, very similar, and the equations are almost the same. in terms of plug in the posterior probability of the latent variables. All right. So, oh yeah, there are some even fancier version. Partially observed data. What does that mean? That means, say you are training HMM, and you collect the data over time, okay? And in some lucky day, that casino vendor is your good friend. He actually told you the sequence and also the outcome. You have the full data. In some bad days, you get a opponent and he's not going to tell you anything. Then you have only the sequence. And but you do believe that they follow the same thing. Maybe the casino had a corporate-wide policy of using that die rolling thing. Then what do you learn? Or how do you learn the model? Very, very simple. In this case, you have a partially hidden data. Your whole likelihood will be made up of these two components. One is the complete likelihood over the entire observed data, and the other is only on the missing data, right? And these two things. Then when you run the EM, you can still run the EM algorithm. In the E step, you are going to do nothing about here and only work on this to figure out the latent variables. And in the M step, you are using the sufficient statistic, whether it is from the real data or from the expected data, from all places, and update your model. Okay, and then the updated model will be reused to do the inference only in here. Okay, so sometimes people will call this co-training, but again, it's a kind of a flexible, paradigm to integrate two types of data. Okay, clear about that? What's that? It is the same thing as the first one. It is converging, right? This is the likelihood, right? And this is the likelihood, and we can basically turn this one into an approximation. It's upper bounded by the complete log likelihood, the expected complete log likelihood. And all the series, because these two things are additive, they don't even interact, right? So if that one is converging, this one, of course, is originally already proven convergent, right? All right, so I have more variants, sparse EM algorithm. So in this space, we become wild and very heuristic. You can imagine, in a wild classroom problem, you have millions of points, and there are some points. Imagine they are already very close to the centroid of the data, or they are very, very far away from any centroid that become outlier, and their posterior probability of the label assignment can be very extreme. They can be either close to 1 or almost near 0. And after you have a few rounds of iteration, you pretty much know the behavior of these points. Do you still want to re-estimate them every time, every iteration? Maybe not, right? So heuristically, you can maybe monitor the rate of change of the posterior over the points. For those which are changing dramatically in every iteration, that means they are really interesting. They are influencing the reassignment of the centroids. Then you really need to keep up with that. For others, which are kind of invariant, they are dead points, you maybe visit them every couple of times, like 10 times or something, right? So these are sometimes called a sparse EM. A pretty heuristic idea, but still have the guarantee of approximate convergence. Generalized EM, I don't know what to say. So in the EM algorithm, many people take on EM as in E, computing a closed form expectation, and in the M step, compute a closed form kind of a sample mean or sample average of the parameters for the parameter estimation. That's in closed form. But it doesn't really mean you have to do that. There are many complicated, say, non-conjugate, Bayesian models, and other model, I don't know how to name it. Maybe a closed form derivation is not possible. Then in the M step, you actually can introduce a macro, which actually does a gradient-based, iterative update in the M step. So in a sense, your E step, you basically impute those Z into Z hat as usual. In the M step, we are going to now do theta of some loss. This loss is now X and Z hat. and then you compute the derivative, and then your theta should be theta equals to theta t plus delta theta, which is computed from here, and you can do it multiple times. Basically, in the m step, you can do an inner loop of gradient-based update, and sometimes you may just loop once, and in every iteration, but still through a gradient, which does not give you a closed form solution of the parameters. And this is sometimes called a generalized EM. So what I meant is that both the E step and M step can be infinitely manipulated the way you want to deal with any surprising structure, right? So like these infrequent updates in here, non-closed form updates, and so on. And that's basically how people practice EM in the real world. So to summarize EM, it's a very, very useful algorithm. You really, really want to master the art of using that. You probably cannot bypass that in your later practice of machine learning because it is general for any model. So the good things are set here already. There's no learning rate. It is automatically enforcing the parameter constraint because it is in closed form estimation. It can be very fast if your parameters are in low dimensional space, and it's guaranteed to converge to a local optimum. The bad thing, of course, is that it is a local optimal algorithm. It can stuck. You need to run multiple times, and it can be slow in some cases if you're, for some hard to characterize loss function. But this, I don't know how to diagnose that, how to correct that. Usually, you only see something wrong when it's already going wrong. So you have to probably restart the program. And the biggest kind of a problem in EM, of course, is this inference step can be very expensive, especially for very complex models. So for example, learning a Markov random field using the EM algorithm can be very, very expensive because in MRF, like an easy model, all the lattices in the model is not observed. And we know that doing inference on that is by itself already intractable. But now you need to use that as a subroutine in every iteration. So that basically makes the whole thing very complicated. Okay. All right, I think that's all for today, and I'm going to see you next week.